Lesson 5-7 on proving quadrilateral properties. Now let's first do a quick review of proofs from Lesson 4-7. Back there, we learned that a proof was a sequence of statements that begins with a given set of premises, or a given set of facts, and leads to a valid conclusion using deductive reasoning. Back in Lesson 4-7, we did proofs on proving triangles and their congruency. Now we're going to be expanding further on that lesson today when proving quadrilaterals and their properties. But before we get to quadrilateral proofs, let's begin first by reviewing a couple important facts that we're going to be using in today's proofs. First, remember that parallelograms have parallel sides by definition. Now, that's an important fact in the sense that in today's proofs, we're going to be doing a lot of work with parallelograms. And so understand that if you're ever asked why a set of lines are parallel, or why a certain quadrilateral is a parallelogram, it's because a parallelogram is a quadrilateral that has parallel sides. That's the definition. You'll see that in use in just a moment. And second, watch for alternate interior angles. Remember back from lesson 2-6, certain parallel lines cut by a transversal will have alternate interior angles that are congruent, and here's how they look. So if we have these two lines that are shown to be parallel, and they're cut by another line called a transversal, then there are angles within those parallel lines on opposite sides of the transversal called alternate interior angles. Now remember, in today's lesson, we're going to be working with a parallelogram. Parallelograms have opposite sides that are parallel. So even if we were to superimpose this parallelogram on the parallel lines and then remove the parallel lines themselves, we still have parallel lines regardless of whether or not they stand independently or if they're part of a parallelogram. And as such, those alternate interior angles inside the parallelogram are still going to be congruent. So let's see in an example proof how all these facts will play out. Let's say that we're given a rhombus ABCD, and we need to show that segments BD and segments AC bisect all these angles. Now you may recall that this is actually a property that we discussed in the previous lesson. Well, let's see now why it's a property. Let's start with the fact. We know that ABCD is a rhombus. That's what's given. Now, from that fact, we can conclude that segment AB is congruent to segment AD, is congruent to segment BC, is congruent to segment CD. Why? Well, think back for a moment about rhombuses. Rhombuses are parallelograms that have all four sides congruent. So because all these four sides are congruent, that's because it's a rhombus. So when something does what it's defined to do, our reasoning or our justification is definition of a rhombus. And finally, we're going to be working with segment BD here. And segment BD is congruent to itself. You'll see why we've actually focusing on that in just a moment. Our goal when proving many of these properties of parallelograms is to isolate, is to find triangles within the parallelogram. And you'll notice if you look up at that diagram that these two triangles here, triangle BDC and triangle BDA, now actually have three pairs of sides that are all congruent to each other. And because there are three pairs of congruent sides congruent to each other, we can conclude that triangle ABD is congruent to triangle CBD because of the side-side-side congruency conjecture. From that statement, we can then conclude that these halves of angles in B and C and B and D, particularly angle ABD and angle CBD, are congruent to each other. And likewise, that angle ADB and angle CDB are also congruent to each other because corresponding parts of congruent triangles are congruent. From those facts, we can then conclude that segment BD bisects angle B and angle D? Because an angle bisector bisects an angle. So if we've proven that a segment does what it's supposed to do by definition, then we can conclude that BD is an angle bisector by the definition of an angle bisector. Now, we're going to take a shortcut here. This same proof, just by changing which triangles we work with, can be also used to prove that segment AC bisects angle A and angle C. So rather than repeat the proof a second time, we're going to take a quick shortcut just saying that the same proof can be done to prove that segment AC bisects angle A and angle C. Thus concludes today's lesson.